Okay, in 2.3b here, we are going to look at quotient rule and higher order derivatives. So for quotient rule here, our guiding question is, how do we take the derivative, or take a derivative, when we have two functions dividing? Okay, and so quotient rule has a somewhat complicated look, but has different ways you can kind of learn or memorize the quotient rule. But so walking through kind of what's happening here first, when you see you have two functions dividing by each other, the lower function, you would write it just as it is. You then would take the derivative of the higher function minus the higher function, just the way it is, times the derivative of the lower function. And then you would divide that entire thing by the lower function squared. Okay? So it's a little bit of a longer derivative to take here, but let me write up how I have it memorized. Okay, so this is how I memorize it, and it has a little saying to it, or a rhyme, or I don't know, whatever you, little song of sorts. And it goes, low d high minus high d low all over low squared. Low d high minus high d low all over low squared. Okay, which you do not have to memorize it that way. There are a wide variety of little songs and memory cues there that exist for quotient rule, but that is mine. Low d high minus high d low all over low squared. Low d high minus high d low all over low squared. Okay, which helps us remember that, right? High or low, just as it is, d high, derivative of the high, minus high, just as it is, d low, derivative of the low, all over my low squared. And I always have a little clap at the end, just to finish out the rhythm, right? Low d high minus high d low, all over low squared. Okay, so here we go, modeling this with a couple of our functions here. So example 1, find f prime of x for f of x. I notice I have two functions dividing, and so I know I'm going to be doing quotient rule here. So we have low, my x cubed, d high, derivative of sine, cosine, minus high, sine x, d low, derivative of x cubed, it's 3x squared, all over my low squared. Okay, and then in terms of what would happen at this point, there's a wide variety of things that could happen. Obviously, if this was a free response, you wouldn't have to go any further than that. But other things that could happen, well, we could literally just kind of clean this up. Minus 3x squared sine x all over x cubed squared is x to the 6th. We also have an x squared we could pull out on top if we wanted to factor out, right? X squared, x cosine x minus 3 sine x. And we could simplify the x squared with the x to the 6th potentially. Which when 2x's cross out of both, the 2x's would be gone in the numerator, and the denominator would have x to the 4th. Okay, and that's quotient rule. Okay, so we're going to walk through 4 more here together, and we're obviously going to practice some more in class. I would encourage you, as I have before, pause the video, try them on your own, see how you're doing, right? Restart the video when you either have an answer or are stuck, but get that gauge as to what you are understanding or not understanding related to the problem. Okay, so example 2 is up next. Find dy dx for y equals, and we have two functions being divided by each other. So we're doing quotient rule. Low d high minus high d low all over low squared. Okay, so low x squared. D high, the derivative of 5x is 5. The derivative of 2 is 0. So 5 minus 0 would just be 5. Minus high, 5x minus 2. D low, we've got power rule down there, which makes 2x. All over low squared. Okay? And again, if it was free response, we could leave it there. But other things that may have happened, they may have just kind of cleaned this up, rewritten it. So this would be 5x squared. And maybe they have it like this initially, minus 5x minus 2. All over x to the 4th. They also potentially could have distributed the 2x there. This would be minus 10x squared plus 4x. And maybe combine the x squareds, right? Negative 5x squared plus 4x all over x to the 4th. There's also an x in common in the numerator. They could have factored that x out. Or maybe even a negative x potentially. I'm just going to factor the x out. And the x and the x to the 4th could simplify, leaving me with just the negative 5x plus 4 in the numerator and an x cubed in the denominator. Okay? Okay, number 3, we have find f prime of x, etc. We notice we have two functions being divided. That means quotient rule, low d high minus high d low all over low squared. Okay, so low, my x squared plus 3x. D high, what's the derivative of cosine? We have negative sign, and that 3 is a coefficient, so it's just hanging out. Minus high, my 3 cosine x. D low, what's the derivative of x squared plus 3x? That would be 2x plus 3. All over low squared. Okay? And again, free response, you could leave it there. Multiple choice, what else might they have done with this one? Well, I could see them having distributed the negative 3 sine x in and the negative 3 cosine x in. So you might look for this, and then minus 9x sine x, minus 6x cosine x, minus 9 cosine x, and all over my low squared. I would be surprised if they foiled that. That being said, one thing they could do, there are two x squared plus 3x's down here, and each x squared plus 3x has an x in common, right? So I could potentially see factoring those two common x's out. And so maybe something that looks more like, give me a second, finish writing my numerator. It's a long numerator. But I could see something more like this, right? So one of the x squared plus 3x would pull its x out. The second one would also pull its x out, so x squared. And we would be left with just x plus 3 left for both of them. And so potentially something along those lines. Let me put a little dashed line here. I've eaten into my example 4 space a little bit. Which is okay. Example 4 has a lot more vertical space than some of the examples do. That way I can separate it there. Okay, example 4. Find dy dx for y equals x squared plus 3 over 8 root x. Again, I recommend pausing the video, trying it on your own. Okay, we see we have two functions divided by each other, so it's quotient rule, low d high minus high d low all over low squared. Okay, so taking my derivative here, low is the 8 root x. D high, what's the derivative of x squared plus 3? And that would be 2x, because x squared would be 2x, derivative of 3, it's a constant, would be 0, and 2x plus 0 is just 2x. Minus high, x squared plus 3, d low, what's the derivative of 8 root x? Okay, remember this 8 root x is the same thing as 8 times x to the 1/2. And so it'd be bringing down the exponent, 8 times 1/2 would be 4, leaving the base alone, subtracting 1 from the exponent. And then all over my low squared. Okay, again, free response, you'd leave it here. Multiple choice, what else might they have done? Well, they could have, first of all, I'd start with cleaning this up. So this would be 16x times root x. Remember, when you multiply like bases, what do you do to their exponents? You add them, right? So this would be 1 plus 1/2, which is 1.5. And then over here, we'd have our minus 4, right, that 4 there, the x squared plus 3. And then x to the negative 1/2 would drop that x to the denominator of that term. All over, squaring this, 8 squared is 64, root x squared is x. So maybe something like that, where all they've done is just kind of cleaned up the function with how it's written, right? Not really done anything else. And then there are a couple of other things that are common. The first one here is one that honestly, for the most part, I'm going to make us do because it's one that we need to practice. It's one that's usually a little bit tricky for people, which is getting rid of the negative exponents. So we did this last unit with our extra denominators. I'm going to multiply top and bottom by that x to the 1/2 to clear that denominator. And so we have dy dx equals, distributing this x to the 1/2 to both terms here. The first term we'd have 16 and then x to the 3/2 times x to the 1/2. Again, one more time, what do we do when we multiply like bases? We add their exponents. 3/2 plus 1/2 is 4/2 or squared. And then distributing it to the second term, the x to the 1/2 will cancel. Down here again, one more time, what do we do when we multiply like bases? We add their exponents. 1 plus 1/2 is 1.5. And again, this step right here is one I'm going to have us practice on pretty much every single one that it's applicable to, because it is one that I know we need to practice. Every year it's one that I know we need to hit quite a few times. So kind of prepare yourself for that. We are going to practice that many times over the next several days. Okay. And so you might then look for that answer possibly. What else might they have done? They might have distributed the negative 4 possibly. Maybe combine like terms there with that 16x squared minus 4x squared possibly, right? 12x squared. Whoops. Went off screen a little bit, sorry about that. So combining, making sure we're good with that. They might have combined these 12x squared. Maybe they factored a 12 out in the numerator, possibly. Might look for that. I don't know, maybe simplified the 4. Right? All of these are just other things that could potentially have happened within the kind of context of your problem here. And you would only go this far, I would say, probably if it was a multiple choice and you had taken your derivative but didn't see your answer. Maybe you had this originally as your derivative up here, but you didn't see your answer written, so then you'd be playing with it, manipulating it to see kind of where else might they have gone with the multiple choice answer until you can recognize the answer you're supposed to be picking. Okay? I guess also, technically speaking, we have a difference of 2 squareds, and so that's just something I saw. I didn't have that on my answer key, but potentially also could have factor the difference of two squareds there. Okay, so lots of things that could have happened. Something you're going to hear me as we get into our kind of practice is asking ourselves that question, what else might they have done? With all of our answers, what else might they have done? So we are prepared to recognize it when we get into multiple choice practice. Okay? Okay, last one with quotient rule here. Find f prime of 1 for f of x. So this time I did give you a number also to plug in. Let's start, though, with taking the derivative. So pause the video, take the derivative of that function, restart it when you're ready. Okay, we have two functions being divided. That means we are quotient rule. Low d high minus high d low all over low squared. Okay, so low, 2x squared plus 1. D high, what's the derivative of 3x minus x squared? And that would be 3 minus 2x. Minus high, 3x minus x squared. D low, what's the derivative of 2x squared plus 1? And that would be 4x plus 0, which is just 4x. All over low squared. Okay, so then we're plugging in our 1. Go ahead and take a moment, pause the video, plug that 1 in, restart it when you're ready. Okay, plugging 1 into this first quantity, we get 2 times 1, which is 2, plus 1, which is 3. Into the second quantity, we get 3 minus 2 times 1, which is 2. That's going to be 1. In the back, we have 3 minus 1. Again, plugging my 1 in. 3 minus 1 would be 2 times 4. All over, down here, we have 2 times 1, which is 2, plus 1, which is 3, which will be squared. Which means that my f prime of 1 is 3 times 1, which is 3, minus 2 times 4, which is 8, over 3 squared, which is 9, which gives me an f prime of 1 of negative 5/9, which is my slope. Okay. Okay, last bit of our 2.3b notes are higher order derivatives. Okay, which we've referenced a little bit in earlier lessons, but we're going to make sure we are good to go with this one. So my guiding question for this would be, what are higher order derivatives? Okay. Well, we've already talked about a first derivative. A first derivative is indicated by f prime of x or dy dx or something like that. Right? It means I've taken the derivative one time. A second derivative just means take the derivative again. Take the derivative of your derivative. Right? And we would indicate that with either f double prime of x or our second derivative. Okay? Third derivative says take the derivative again. Third derivative would be f triple prime of x, or the third derivative. And this means take the derivative of your second derivative, which you get by taking the derivative of your first derivative, which you get by taking the derivative of your function. Right? So all of these just means take the derivative of what you've just found. And this could keep going on and on and on and on. We've got fourth derivatives, fifth derivatives, 12th derivatives, right? But goes all the way until the nth derivative, which would be f of n, right? N primes, however many derivatives you need to take. Fifth derivative, that would be a 5. Seventh derivative, that would be a 7, right? For our nth derivative there. The only thing you need to be careful of, well, I shouldn't say the only thing, but one of the things you need to be careful of with higher orders derivatives especially is watch out for, and I always call them new resulting rules. What I mean by that is this. There are times where initially when you look at a function and you take its derivative, it might be, you know, power rule or maybe product rule or something like that. But then, or maybe a trig, right? It's a basic trig rule. But then after you take that first derivative, as you are then looking at taking the second derivative, you might notice that all of a sudden now you have two functions being multiplied where maybe you didn't originally. If that happens, you need to be careful, right? That's what I mean by new resulting rules. It's not like it's actually a new rule to you, but maybe it's a new rule to the problem. Maybe you haven't already used product rule, but after having taken a derivative, then you notice you have two functions now multiplied, which means you will have to do product rule, right? Or maybe you didn't originally take quotient rule, but after taking the derivative, then you notice you have two functions being divided, meaning then you have to use quotient rule, right? So watch out for those new resulting rules. Make sure you always pause and take a hard look at the derivative you will now be taking. Is there a different rule you will now have to use? Okay, and you're going to see that already in one of these problems. Okay, so I'm going to walk through one here, and then my encouragement to you would be to pause the video and try the others, restarting them as you have answers, right? Example 1, we are finding the third derivative of our function, which is negative 3 root x, which remember that root x is the same thing as x to the 1/2, minus 2. Okay, so to take the third derivative, I first need to take the first derivative. Okay? So go ahead and think for a second, what's the first derivative of negative 3 root x, or negative 3x to the 1/2? And I'd bring down that exponent, leave my base alone, and subtract 1 from my exponent. And think for a second, what's the derivative of 2? It's a constant, so that'd be 0. So here's my first derivative. Okay, I need to get to my third derivative though, so I need to take my second derivative now, which means taking the derivative of my first derivative. So take a hard look at that. Is there a different rule other than power rule or constant rule that I'm now going to have to use? And for this one, no, this is still power rule, right? So bringing that exponent down in front, we would have 3/4. Leave the base alone, subtract 1 from the exponent, which means now I'm ready for my third derivative. Again, take a hard look at it. Is there a new rule other than power rule or constant rule, which are the two we've used so far? No. So bringing down that exponent in front, we have negative 9/8. Leave the base alone, subtract 1 from the exponent. And that's your third derivative. Okay? Okay, so again, I'm going to recommend example 2. Pause the video, try it on your own, restart it when you're ready. Okay, fourth derivative here. We have y equals cosine x. So what's my first derivative? What's the derivative of cosine? And that'd be negative sine. Okay, second derivative then. We have negative as a coefficient, so it's going to hang out. What's the derivative of sine? That would be cosine. Third derivative, we're trying to get up to the fourth derivative here. Third derivative, that negative is a coefficient, it's going to hang out. What's the derivative of cosine? And that would be negative sine, so the two negatives would make a positive. Whoops, third derivative. And then fourth derivative, one more. Fourth derivative here. Okay, what's the derivative of sine? And that would be cosine. Okay, last one, example 3. Pause the video, give this one a shot, restart it when you are ready. Okay, so we want a second derivative, which means first derivative is up first. So derivative of cosecant x is what? That would be negative cosecant x cotangent x. Right? And then we are up to second derivative, and right here, this is what I was talking about. Watch for new rules. Take a hard look at that derivative. What rule are we going to have to use besides our cosecant derivative, which we've already used? And some people might say the cotangent derivative, which is true, that's also a new one, but there's another one we need to make sure we catch. How are these cosecant and cotangent attached? They're attached through multiplication. This right here, negative cosecant x and cotangent x being multiplied together, is product rule. Okay, so 1d2 plus 2d1, we have 1 negative cosecant x. d2, what's the derivative of cotangent? Negative cosecant squared x plus 2 cotangent x. d1, what's the derivative of negative cosecant? Well, the negative would be hanging out, and the derivative of cosecant is negative, so the two negatives make a positive, cosecant x, cotangent x. And so that's my second derivative. This would be the two negatives canceling, cosecant cubed x plus, and the cotangents would combine, so cosecant x, cotangent squared x. Okay. And those are higher order derivatives. Okay, if you have any questions, write them down now. Make sure you're ready to ask them when you come into class.